Welcome back, David. Change of scenery for you.
Yes, I am. I'm in the tropics.
And this brings me to a topic that I want to kind of bring up is the spectrum of lights and what are they, how they differ. And more often than not, what people don't kind of miss out, myself included at the beginning, is that spectrum in light doesn't necessarily mean something you can actually see. It's just there.
Very,
So
very true. Yes. Let's start there, right? Let's start there. Let's define light, right? Because most people think light. Well, let me just share my screen so we have something to talk to. Um, just give me a moment there and we'll go with that. Let's see here. Share. Perfect. Okay, so you should be seeing this electromagnetic field spectrum. And essentially, that's what we're talking about when we talk about light, or anybody really, like whether they know it or not. When they say the word light, what they think is this little exploded part here down at the bottom, which is the visible spectrum, right? Which is basically that means that's what our eyes are allowing our brain to see, right? And that's the rainbow, right? Everybody kind of knows about that. 400 nanometer light, right? So these are frequencies that we're talking about, and nanometers represents the actual measurement of the frequency. That's all these numbers mean. We can see if you look at the very top, a very high energy frequency. That means that the squiggles here at the top are moving very quickly, and as you move to the right, you'll see that the wavelengths get wider and bigger, right? So that if you look, where is that? Right here. If you look right here, right, we have radar, microwaves. We also have UHF and VHF. So these are basically radio frequencies. That's what these are, right? So these are big frequencies. You see the big waves right here, and then small waves over here, right? And that's where we have X-rays. That's where you have gamma waves. They have a lot of energy, but they are not going to penetrate very far, right? So if we look at the light spectrum from this point right here, this way, these we cannot see. And if we look at this spectrum from right here and this way, these we cannot see. So just like you
that's
pointed out,
very, very small portion of it all.
very small, right? So now when I say light, I'm talking about the whole thing, right? I'm talking about the whole thing, the things you can see and the things you can't, because they're the same. The only difference is that your eyes biologically have been tuned to only see that sliver, which brings us to the main point is, do these specific frequencies, right, the nanometers, do specific things in the body? And the answer is yes. But I wanted to highlight something that's not on here, right? And that is this. Our atmosphere also shields us from these, right? So our atmosphere shields us basically, you see right down here, I'm going to circle it. It says UVA, UVC, B, and A. And there's a little line that comes right through here. That line cuts off UVC and down, right? So from UVC down to the left is not let through the atmosphere, right? And then if we come right over here, right around this point, this way, that's also not let through the atmosphere. That's like radar, UHF, VHF. Those are all of these, right? From that don't get through the atmosphere. They're being put out by the sun, right? So the sun is putting out X-rays, gamma rays, shortwave radio waves, and alternating currents like this. That's all in space, right? So if you were to go out into, an astronaut, you're going to be exposed to the full frequency. But when you're on Earth, you're really only exposed to this chunk right here, which is slightly bigger than our visible spectrum. What that means is this: our biology also uses frequencies that we cannot see. Right? So if I were to get rid of this drawing and clean it up just a little bit, it looks like a box like this. Boom, it comes all the way to here. That is the range that our biology interacts with every single day when you're outside, right? So now let's get into that, right? Are there specific frequencies, specific frequencies of light that our biology has been tuned to? And the answer is yes. Let's start talking about the ones that matter the most. The thing that matters the most is our mitochondria. That is literally the thing from what we talked about literally in our previous episode that just got released. The mitochondria are energy transformers, right? And we have trillions of them. They are tuned and can be amplified or degraded depending on what frequencies are interacting with them. We'll talk about the frequencies that matter the most in terms of if that frequency, and it's going to be color. So when I say a color, it also means frequency. And when I say a frequency, it also means color. For the sake of this video, we'll just talk about colors right now to make it simple for people to understand, right? So things that we know for a fact. They've been studied in mitochondrial health and mitochondrial biology, and even in cancer research and stuff like that, because I don't know if people know this, but we have officially, right, this year, 2024, 2025, there have been some studies that have been able to be replicated and solidified that cancer is not a genetic disease, right? So they have officially, the leading cancer experts have officially said that, because they have found cancer cells that don't have any gene mutations. And they've been able to take a nucleus from a cancer cell and put it in the nucleus of a good cell, no cancer, and a nucleus of a good cell back into a cancer cell still exists. So it's not about the genes, right? We have officially confirmed genes do not make cancer, period. End of story. So what does make cancer? Mitochondria. Mitochondria makes cancer because mitochondria uses fat metabolism inside the mitochondria. That's called phosphorylation or fatty acid oxidation. A couple different names there, but basically what it's doing is it's taking fat inside of the mitochondria and burning it. That's what the mitochondria does, and it dramatically extends energy expenditure. But when it's ruined, glycolysis and the pentose phosphate cycle exists outside of the mitochondria, and that's what ancient life used to use before mitochondria as far as energy production. And that's what they're distinguishing now. That disconnect of mitochondria becoming unhealthy and now they can't use fat metabolism, that's actually what causes cancer and the genetic mutations at the genomes. A little bit of an offshoot, but it really matters to what we're talking about right now, because I'm going to bring up another little slide here in just a minute as soon as I find it. But while I do that,
you're opening a big can of worms there.
I know. Yes, I know. But while I do that, let's see here.
Because from all the previous videos, what we talked about and how you highlighted out that different light can affect what kind of even metabolism your body will kind of. What I'm saying is either preference for carbs or fat might be dependent on what kind of light is out there. And then we have these centers coming up now where, come in, we're going to heal you with frequency. And more often than not, they don't even understand what they're doing.
Correct, right? Because we're just kind of in the infancy, right? Like basically up until these few studies in the last few years proving that it's a mitochondrial thing, nobody's really been focused on what changes the mitochondria. Like what does specific frequencies of light do in the mitochondria? So we've been not really on top of it as far as science of like deciphering that stuff, because up until recently, we've been focusing in the wrong place, right? So
probably because you can't make money out of light.
Well, it's very difficult, right? You almost have to pitch somebody a very half truth, right? It's not a full lie, because you're telling them some things that actually happen, and that you're not telling them some of the truths of like why or how it needs to be combined and that sort of stuff, right? So right now you're looking at a very simplified diagram of the mitochondria, but mainly this is just so that we can talk to it, right? So this is cytochrome 1, this is cytochrome 2, this is cytochrome 3, and cytochrome 4, and then the ATPase, right? You don't really need to know the details of it or anything like that. That's not really what we're here to do. What we're here to do is, I'm here to show you that Cytochrome 1 is amplified by specific frequencies, and we'll talk about what they are. Cytochrome 2 is as well. So if you go, and I've gone ahead and put a little, how would I say, box here so we can break things down, right? Complex 1, it has an affinity for flavins. It's made out of flavins and stuff like that. That's the chromophores. Chromophores means it gathers light. It gathers specific colors of light, and that's why they call them chromophores. The color that sensitizes it is it's sensitive to UV and blue light. So what does that mean in terms of energy production? That's the it's the NADH molecule. Where do NADH come from most? Carbohydrates. Right? What does this tell you? That UV light and blue light are dominant in that environment where there's going to be a lot of carbohydrates, aka a lot more NADH versus FADH. And when you're doing that, you should be in that environment as well, right? Like if there's lots of carbs growing out in that environment, you're probably in that environment as well. That's not a coincidence. That is how nature has set it up. And so what it does is it amplifies the environment outside that grew the plant, also amplifies directly complex 1, which is going to deal with that plant's chemicals. Let's put it that way, right? The molecules that are coming from it. And UV light and blue light make it more sensitive. Making it more sensitive means that it's going to go through its actions of dismantling NADH into NAD plus and pumping protons. What does that mean? That means you're going to increase reactive oxygen species, and you're going to potentially oxidize more stuff, right? Because you're using more oxygen in that capacity. Now,
you're going deep, and can you just pull back and a little bit, explain what reactive oxygen species are and oxidation and all that kind of stuff? Because in my head, I can see what's happening because I see electron transport changes spinning there. But for some people, they were like, what the hell you just said?
Yeah. So reactive oxygen species are not bad, and they're not good. They are a signaler, right? So what this means is, think of fire, right? When you have excess energy, you have oxidation going off and kind of making flame and excess heat and all of this stuff, right? Think of it like a fire, right? If the flame is very controlled, right? Kind of like what I talked about the last podcast that we did, when you control a reaction very, very, very tightly, there should be very little heat loss or entropy. That's what it's called in physics, right? Is the energy used to move that is very concentrated, and most of it stays only where you want it, right? Think of it like a very efficient engine. But when there's a lot of excess, like a fire, it's just open and letting out all its radiation, its light, its heat, everything like that. Think of that like excess ROS. You're never going to make it zero, right? There isn't such a thing as 100% efficiency in this world or in this universe. There's always entropy. There's always loss. So ROS is reflecting how efficient cytochrome 1 is, right? Lots of ROS, very inefficient cytochrome 1, lots of radiation, let's just call it that, right? Lots of heat loss, lots of energy loss. But in the body, that would kill things. That would kill your mitochondria. That would kill your cell. So it doesn't let it just become heat and chaos. It concentrates it in reactive oxygen species, which are paramagnetic. I'm not going to go in way more detail than that because that involves like electrons and atoms and their spin, right? Like it involves like how much or what they're doing involves that type of talk. We're not going to do into that, but I'll say it like this. Excess of reactive oxygen species is going to amplify inflammation, right? That's very like downstream, that's where it ends, right? The right reactive oxygen species, because they're paramagnetic, causes a specific magnetic field that causes growth, right? So think of it this way. Lots of carbs in the environment. You're amplifying the complex 1. You're going to make the right amount of reactive oxygen species. What does that mean? That means that if you're damaged in any kind of way, say working out or exercising, when you repair, that amount of reactive oxygen species is going to create a very specific growth response, right?
That's what I wanted to get to. Because a lot of
Yes,
people
yes.
kind of don't pick up on this, and I have this conversation very often with people I work with, that their elbows hurt and knees hurt and this and that, and then we start breaking down their daily habits, and to them it does not kind of put together in head. Like what you explain is basically, if, correct me if I'm wrong, is if you're consuming certain nutrients, then cause certain stress, but your mitochondria is inefficient to kind of get dealt with those nutrients, and you create too much reactive oxygen species and don't expose yourself to correct light, or maybe expose yourself to incorrect light, which is like laptops, 5G, and so on and so forth. Now you cause inflammation, now your elbows hurt, your knees hurt, and so on and so forth.
Correct. Correct. That's 100% correct. That's why we started with complex one and blue light. Most people have too much blue light compared to others, because once we get into the other frequencies of light, you'll understand how some of these correct the reactive oxygen species problem and all of those things, right? So now we'll go to complex two. Complex two has to do more with fats and yellow and green. It does have a little bit of blue fade in there, but it starts to move up into the 500 frequency range, which is green and yellow. And
So when you
those,
say blue, you green, yellow, is this that we see, or is this one still that we just
no,
feel?
these are ones we see. These are ones we see, right? So this is 450 nanometer light is blue. So when you see a blue light, blue LED, it is in that 450 nanometer range. When you see a green or yellow, it's in that 560. That's clearly within a visual. So all these ones that we're talking about right here, they are visible. We're talking about visible things, right? The color, right? We're talking about the rainbow. So
It
you
reminded
can
me to
see these frequencies.
put my screen in night shift so I don't have so much blue.
Yes. So green stabilizes hemes. Hemes are basically everywhere in your body. That's red blood cells. That's cytochrome P51, P450. That's all. They stabilize. Green and yellow stabilize these heme proteins. What does that mean? It makes it so that they are able to do their job efficiently, just like cytochrome 1 gets stabilized by UV light. And so if you're missing green and yellow, you're destabilizing heme proteins, and that's a big problem. That's a very big problem. Now, I don't know if people know this, but LEDs, like when you go buy LEDs, there's no green and yellow in them, right? There's only blue and then covered with a specific film over it that basically sequesters. That's how they make white light out of blue light, right? It basically fades it all out, and you get some green and yellow, but it's not very powerful. It's mainly blue. If you were to get a spectrometer, you would see a gigantic spike in blue, and then there is the other colors, but they're significantly less. And basically, like if you look at my head, the spike goes to the top of my head, but the rest of the colors are down here at the bottom of my jaw, right? There's a big drop off. That's how LEDs are built, and that's how they or make these other colors. It's like a piece of plastic that they put over it. That dome that's on LEDs, that is a white dome, so that it makes it, when the blue light goes through it, it kind of disperses like a prism, right? When sunlight goes through a prism and makes all the rainbow colors. This works in reverse. This plastic, this special plastic, blue goes in and white light comes out, which has all the colors kind of embedded and melted into it, but there were significantly less. Then we go to cytochrome 3. That's going from green, yellow up into the higher, close to 600. So we're starting to turn orange and red. That's cytochrome 3. Again, that has to do with altering hemes, but also ubiquination, right? Ubiquination meaning the marking of things, right? Like what is good and what is bad, what needs to be recycled. So these nanometers of yellow into orange, they start to amplify or optimize those processes that are going on biologically. And then towards the very end, cytochrome 4, which is where you're going to take oxygen and combine it with hydrogen and make water, cellular water. This is a big topic. This is the deuterium depleted water that your mitochondria should be making, and all of those types of things. Those are amplified by things that we've said before: red light, infrared light specifically, in the 700 to 800 nanometer range. And then the visible red that we see, that we can physically see with our eyes, is 600 all the way up to like the top of the 600 range, right? In the 600s. That's the color red. And the near infrared is, we cannot see that. That's just above 700, 750, and then going all the way up into the 800s and up. Those photons interact with complex 4. They're going to amplify water production. They're going to amplify ATP production. They're also, because they amplify water production, it makes it so that higher ranges of infrared light. So now we're talking into the 1000s, 2000s, 3000. Those infrared versions are heat, right? That's actual heat that you can feel. Water helps store those, right? That's how you can stay warm-blooded with very minimal inputs from energy, is because the water in your body collects heat and stores it. And that's actually one of the unique characteristics of water on this planet, is that that's actually how we measure calories. How much energy does it take to move 1 gram of water 1 degree Celsius, right? That's a standard thing, because no matter what environment water is in, it always takes the same amount of energy to move it 1 degree up or 1 degree down, right? And so it's very hard to accelerate that or change that. Like metals and other things, depending on their environment, you can and some of the molecules, you can dramatically change how much heat they suck in and how much heat they release back into the environment. You can't do that with water. That's why it's used in this process here to create all the cellular water in your body and all of those types of things. Then we go down to the ATPase. There's no direct chromophore here, but because these other colors amplified cytochromes 1 through 4, now you're pumping a lot of protons, right? When you pump a lot of protons, now the ATPase spins more. So these colors directly affect the efficiency of ATP, because ATP is dependent on the pumping of these cytochromes 1 through 4. That's about as complicated. I mean, it is very complicated. It gets more complicated, but that's as much detail as we really need to get into, like the colors, right? Now let's talk about the things we can't see, right? We talked a little bit about infrared light and stuff like that. We can't see the higher end spectrum, and it clearly affects ATP production and biology. But as you just see right here, right? If reactive oxygen species is really high, let's just say somebody comes to you and has a lot of inflammatory markers, the very first thing you want to look at is, well, how much UV and blue light are you getting, right? If you're getting a lot of blue light, but no UV and no infrared, well, then I would expect a lot of reactive oxygen species. And because you're not getting very much infrared, I would expect very little water production, or not optimized water production, I should say, at cytochrome 4, which would mean that you can't quench reactive oxygen species very easily. That's a big deal. So when you have all these other colors, right? Blue all the way through orange and red, combined with a lot of infrared, then you're going to essentially be optimizing the whole system together. Now, there's one important thing to understand about red, and this is from physics. We, other than cytochrome 4, and again, cytochrome 4 cuts off at like 830. So anything above 830, we don't have chromophores for. It's more like, how would I say it? Scattering. It's called scattering, right? So basically what this means is, when a photon enters the body that's from the 830 and up, it bounces around in the body before it leaves, right? What does that mean? That means that it loses its energy in your water, in your cellular water, before it leaves the body. Right? We have lots of studies on this from physics and stuff like that. Every single infrared photon that enters the body will eventually leave the body at some point in the body, but it never goes straight through, because it scatters. Because there's no chromophores to suck it in, it bounces off of everything. It bounces off of everything. So think of it this way: like if I have a photon that enters my head right here, it's going to bounce around in my melon because it's full of water, and it's probably going to leave somewhere else, and it may have taken a full meter of distance before it actually left, right? Because it bounced around so much, the distance that it covered was very, very far. So that gave it a lot of time to dissipate its energy into my body. But because of physics, energy can't be created or destroyed. So that energy that it's letting off in my body is cascading and vibrating in my body, and your body has basically it's solid, right? You are like if you touch yourself, you're solid. So that means that it can hold tensegrity and energy vibration, right, which is another form of energy collection on top of radiation, on top of all the other things that we've talked about, like cold amplifying energy production and all of those types of things. So that is really the thing that infrared light does. It does a lot of scattering inside the body that amplifies vibrational energies in the body and at the same time improves water production and water networks in the body. It makes you more cohesive. The crazy part is this. From the sun, you get almost 90% infrared light in that range. Right. So that is a major thing to understand. When we were talking earlier about this box that biology is optimized for, now you start to see why it looks the way it looks, right? UVC all the way up here into the 3000 range, right? So this little box right here, we can't see any of that, but it's pretty big compared to these lower sections. That means that it has a lot of input into the body under normal conditions. It so happens that now we live in the modern world where basically this box has been erased out of most people's lives, which means that you don't get a lot of scattering, you don't get a lot of water optimization, you don't get a lot of ability to sequester reactive oxygen species, all of those things, right? That is basically a deficiency. That's what's called a nutrient deficiency. The difference is it's not a nutrient that people talk about very much, right?
Can I
Or how it even
dump it down a
interacts.
little bit?
Sure.
Because basically what you're saying is that we have created environment where we have a lot of inflammation, either physical, mental, because we know when you think, you probably spend most of energy just by thinking. And so there is byproduct, no matter what we do. There is resource and there is whatever comes out of it. But now we have, over the last 20, 30 years, it depends on the country. You know, the more advanced countries, the longer it has been, we have lost the ability to recover, basically. This is why we have so much fatigue. This is why we have this so-called metabolic syndrome and whatnot, where we just gain weight from supposedly nothing. Mental health issues, and so on and so forth. This is why. Was it Japan that prescribes you go to the forest when you feel depressed?
Yes.
One of those countries.
Yes, it is.
You
yes.
know, and you and myself, we both know, like, when we go in nature, you feel better. It's basically not as much nature, but as much as being away from everything else and getting our body back in balance. And it also makes me question, like, people who are using these advanced tools now are more often than not people who don't spend much time in nature at all. And they benefit from it the most, right? Okay.
Yeah, they'll be more sensitive to it, right? Like if you're infrared starved or any of these others, like green or whatever, right? Like if you add that in, yeah, you're going to get a benefit. But because you can't control how much you're adding in, like you can't see, hey, let's talk about green, for example, right? Cytochrome 1, 2, and 3 are all green related, right? How much green are you getting? Can you actually go look at those cytochromes and see if they've been optimized or not? And the answer is no, you can't. We don't have that technology yet, right? Like now we have the technology to create the frequency, right? We can create as much green as we want. We can create all of this stuff, right? We can, and you know, I just told you how beneficial it is for these. So then you take that idea, you amplify the green, you give it to somebody. If they're deficient in green, they're going to get a positive, and then guess what will happen? When you get too much, then they'll get negatives. That's called a biphasic effect. All light is biphasic in effect in the body, meaning you need it just right. Right? You need it just right. That's the main thing people got to understand. Will we eventually make the right light that you can put in your home? Maybe, if people get obsessed enough with this and get the right tools to get the right feedback.
Let's be honest,
right?
we probably already had it.
Well, yeah, we might, right? We just aren't using it or haven't been told about it or et cetera. That could be totally true, right? I'm not, again, technology is much more advanced than what the population actually gets to use as far as like what's actually out there. So yeah, totally possible. as far as like readily available to the average person, that even people that have a lot of money, mm, probably not quite yet. And that is a big cautionary thing, right? So now let's talk about light, like human-made light, right? LEDs, incandescents, all of these types of things, right? Now, LEDs, like I just mentioned earlier, right, are primarily blue, a little bit of the visible spectrum. They're really good at doing that. They have zero infrared or red, really, other than whatever's being put out by the white light. They have zero UV of any of those. And so it's very narrow. And what it does is it only optimizes like 2 or 3 cytochromes, and the rest of them get left off, right? So you're basically amplifying reactive oxygen species side, right? Because if you go, if you kind of rewind this video and you look at the ones that are affected by blue and green, they all have to do with reactive oxygen species. None of those frequencies have to do with producing water and sequestering the reactive oxygen species. So you're essentially setting yourself for a lot of inflammation if you only use LED lighting. Right. That there's a lot more to that as far as other things that can happen, but that's the very simplest form to just kind of think about it. Now, when you start adding in infrared, right? Now, we have lighting before that did a lot of infrared and very little? Yes, that was incandescent bulbs. Incandescent bulbs actually reflected very closely what the sun does. The sun is primarily red and infrared, and you get a little bit of the visible spectrum and a little bit of UV, right? 10% of visible and UV, and the other part that you're seeing me hit my body right now is all infrared, red and infrared. That's how incandescent light bulbs are set up. If you put a spectrometer up to an incandescent bulb, it'll be very similar to sunlight. Not identical, but very close. A lot of infrared and red, a little bit of visible, and a little sliver of UVA. No UVB or anything like that. So not quite sunlight, but very, very close. Halogen light bulbs, again, very similar, but also not quite. So I'll describe what a halogen has. A halogen, just like a incandescent, has a lot of infrared, a lot of red. It has the visible spectrum, a little bit of UVA, a little bit of UVB, and a sliver of UVC. So it actually has a little bit more UVC. Now, would that be beneficial, right? Like in certain circumstances? Yes, because it's going to allow you to create melanogenesis and creation of melanin because of the extra little bit of UV it has. Now, would I use those at night? Probably not, because it has UV. You see what I'm saying? The halogens are, in my opinion, pretty good, and incandescents pretty good in the day, right? Like if you're in an office and you have the option to light your office because you're going to be there and you work there 8 hours a day, halogens and incandescents are going to be probably the best thing. Now, if you have windows, I would say combine some incandescents with opening the window, then you get the full actual benefit, right? And the reason for that is because of this synergy, right? We don't know the feedback. Is this extra little bit of UV that you're getting from halogens going to not optimize this? That's what we don't know, because we can't look into the mitochondria and see, did we optimize it correctly? Now, can I tell you, is it going to be better than an LED? 100%, because you need those frequencies. You're giving them some. Are they optimized? That's what we don't know. Right? So there's a difference between I'm going to give you something that'll probably help you versus I'm going to give you something that's going to optimize you. Those are two different talks there, right? The only thing that I can guarantee that can optimize you is sunlight, because that's what your body was created to use. But we can add in these slightly different variations that have all the things that you need. We just can't quantize exactly how much and whether you need more or less. Now, LEDs are absent, right? They literally do not have infrared or UV. So I can tell you without a doubt that that is subpar light, right? It's deficient, right? Deficient in nutrients, right? Think of it like incandescents and halogens as fortified foods, right? Foods that we know are missing some nutrients. We've added the nutrients. Now you should be okay. Does it work 100% of the time for everybody? No, but it works most of the time for most. You see what I'm saying? That's what incandescents and halogens are. That's how you should think of them in relationship to food. And think of LEDs like sugar, literally like sugar. You've taken everything away and we're only delivering the deliverable, and that's it, right? There's no other benefit other than now you can see, and that's it. But it does nothing for your biology. And that's exactly what sugar is. It gives you glucose and nothing else, right? Nothing else. And we know that that's subpar, right? So that's what LED is. Think of it like junk food, incandescents, and halogens. Think of them like fortified food, slightly better, probably pretty good, okay for you, but not the best as a full-fledged, from the farm vegetable or from the farm cattle, right? That would be the equivalent to sunlight and sunlight only.
It explains a lot now, and it makes me kind of think like, okay, there are a million follow-up questions. Obviously, when is one light better over the other? Because there will be some instances where actually some light might not, like carbs. For majority of people, not a good idea. For someone who is extremely well trained, probably best thing after, I don't know. You know what I mean?
Yes. Yeah.
So,
Yeah. Let's highlight that real quick, right? So that comes down to a couple things. First, let's talk about the brightness. The brightness of the light also matters, right? Because the brightness also kicks off circadian switches in the brain to tell you, is it clearly daylight or not, right? And that's around 10,000 lux. Now, the sunlight, like once the sun gets out of this cloud here, that's going to easily reach 20,000, 40,000 lux, way, way above that 10,000 threshold that actually trips the CNS to tell you that it's daytime. So the brightness of light matters to clearly tell night from day, right? Now, if you're in a mono lit room, meaning the light never changes in intensity all day, your body has a hard time understanding what's day and what's night. That starts to mess with the circadian mechanisms of day and night. So the intensity of light, the brightness of light, which is also called lux, actually gives you the on and off switch of night and day. That's very important to never mess up. And what that means is during your waking hours, it should be the absolute brightest that you can make it. You're probably never going to be able to make it brighter than the sun. So that's going to be obviously the brightest thing you can do. But the brighter, the better during waking hours. You got to flip that whenever the sun goes down. You want to make it the dimmest that you can make it while still being able to see before you go to bed so that you can clearly trip that switch. That's really all you really got to understand about brightness of light. There's a couple other things that have to do more with like specific problems like sneezing and sneezing problems and hiccup problems. That's a different talk.
like I said, there is a massive kind of worms when you start talking about this.
Yes, there is. And then the next thing, right, is light hygiene. Now that I briefly talked about it here just right now, which is exactly what I said. Reflect what's going on outside. When it's sunny outside, make it as bright as possible, make it as close to sunlight as possible. That's great daytime hygiene. Nighttime hygiene, flip it the other way around. You want to reflect it more towards what you're going to be getting from the planet, which is very little visible and a whole lot of infrared. The more infrared, the better. Why? Because all the rocks, all the grass, all the cement around me, all these buildings around me, everything was interacted with the sun during the day. And when the sun goes away, visible light goes away. But guess what? All of these things are going to radiate all that infrared energy back into the surrounding environment. You're getting a ton of infrared even at night as the sun goes down, even though the light that you can see goes away. So infrared becomes the dominant energy source into the evening hours. You want a lot of infrared in the evening hours so that you can hydrate the body right before you're going to go to bed into a dehydrated state. You're not going to eat, you're not going to drink, etc. But it's going to power all these cells and keep them hydrated so that they can do all the return processes, all the recovery processes.
Awesome, David. I know you're on holiday and you need to run off, so appreciate your time as usual. I'll see you in next video. And it has opened up a million topics to follow up.
Awesome, man. Thank you.